So the today's topic for the lecture is development and hardware prototype of an efficient method for handheld arrhythmia monitoring device. So the main aim of this lecture is to develop a ECG monitoring system which is capable of detecting the diseases in real time at the place of patients itself. So for that, several methods have been proposed, they have been published, they have been simulated, and then after they have been implemented on commercial available microcontroller platforms as well as FPGAs, and then after it has been customized into a small device which is handheld, and the resulting system is known as the Arrhythmia monitoring system or device. So I am associated with the Department of Electronics and Communication Engineering, as said by our Honorable Dilip Chaubey sir. So first of all, what is the motivation behind selecting this topic? So let us come to a brief history of this, that the cardiovascular diseases are the leading cause of death in the world, as per a report which was published by WHO in 2013. Coronary heart disease has risen from 1% in 1960 to 11% in 2003 and 14% in 2011 in India's urban population, as per the article published in Times of India in 2014. Recently, several surveys have also been done, like life lost due to the cardiovascular diseases in India has been increased by 59%, from which is 23.2 million in 1990 to 37 million in 2010. So what do we want? So we want that any patient or any subject should not die. He should avail the primary healthcare facility. So regarding the facilities, what we have currently available, that around 60% of hospitals in India are located in the urban areas and cater to only 30% of the population. And only 13% of the rural population have access to the primary healthcare facility and less than 10% to hospitals. So this is also published in Times of India in 2011. So the cardiovascular diseases, to detect the cardiovascular diseases, we have to analyze the ECG signals. One of the most important things that I forgot is, as per the report of WHO also, this cardiovascular disease will remain the leading cause of death across the world till 2030. So to analyze this cardiovascular or to detect these diseases in time so that a person should not die, the basic tool which is used to analyze these kind of diseases is known as the ECG or the electrocardiography. So ECG is a graphical representation of the bioelectrical signals, which is used as a non-invasive diagnostic tool to interpret and determine the medical state of the heart. So it is a non-invasive. Non-invasive means we are taking the input over the body. We are not implanting. There are two kinds of diagnostic tools. One is invasive. Invasive means we are planting something inside the body, and non-invasive means we are not planting inside the body. Instead, we are placing some kind of electrodes, as in the case of ECG. We are placing the electrodes over the body, and we are interested in measuring or gathering the ECG signals, and that are being interpreted by a cardiologist to determine the medical state of the heart. So To detect this signal, first of all, we should know that how a heart functions. So I will not go in much detail that how a heart functions, but typically I will try to brief myself in a couple of minutes that typically a heart consists of four chambers. These two upper chambers are known as the atrias and the lower two chambers are known as ventricles. There are two nodes through which the blood pumps inside this heart, that is the upper chambers and the lower chambers. And there is also a node which is in between the atrias and the ventricles, through which the blood moves from the atria to the ventricles. So this is the sinoatrial node in which, and this is the atrioventricular node, AV and SA. Sinoatrial node is known as the sinus rhythm of the heart because through this node only the blood comes inside the heart. As a result, this flowing of blood through this chamber results in the generation of three processes. The first process is known as atrial depolarization. Second one, ventricular depolarization and ventricular repolarization. So as a result of these three processes inside the heart, these three processes generate three different kind of waves. And on together, these waves constitute a single ECG signal. So due to atrial repolarization, we can see in this table that due to atrial repolarization, where the upper chamber contracts and so the process undergoing under the atrias or the upper chambers is known as atrial depolarization, and P wave is generated as a result of this atrial depolarization. So whatever the waves are being generated, like due to ventricular depolarization, the QRS waves are generated, and in the ventricular repolarization, the T wave is generated.
Excuse me, sir.
Sir, your slides are not changing.
Sir, your slides are not changing.
Now it is visible?
Yes, sir.
Yes, sir.
Okay. So let me make this a bigger one. Now I think it is clear?
Yes, sir.
Yes, sir.
Yeah. So as a result of these three processes, the consecutive waves are being generated like P, QRS, and T. And each of these waves generated has their own amplitude and period, that is duration of their occurrence. So any deviation from these values, either in amplitude or in period, results in the generation of abnormalities inside the heart. So if there is any problem in the generation of T wave, which is the clinical significance, that if there is some problem in the atrial depolarization, the upper chambers, if the upper chambers are not working well, then this may lead to atrial enlargement, fibrillation, or flutter. We will discuss fibrillation and flutter a bit later. It has its own clinical significance. Actually, it is based on the heart rate. So when I will classify the abnormalities, I will discuss there. So the amount of time the blood is in the sinoatrial node and it is moving from the atria to the ventricles, there is a delay at the AV node, which is the PR segment, means the line, the isoelectric line joining the P wave and the QRS wave. So if this has some kind of blockage, there is a possibility that in the node, during the flow of blood from the upper chambers and the lower chambers, then it may result to heart blocks and atrial tachycardia. So ventricular depolarization has a clinical significance of ventricular hypertrophy, myocardial infarction, and many more. Similarly, when the ventriculars repolarize it has a generation of T wave, and its clinical significance is coronary ischemia, wellness syndrome, left ventricular hypertrophy, and hyperkalemia. So the ECG is being classified to normal and abnormal based on the amplitude and period of each wave generated. So as I have said that if there is a variation in the amplitude, so every wave have its range and it depends on human to human. Suppose if I measure my heart rate at this time, it may have 85 or 90. This is my normal heartbeat. But if I measure your heart rate using some kind of device, it may be 72, 75 or 80 or 95. So this has to be justified that what is normal and what is abnormal. So classification of arrhythmias, how they are being classified. So they are classified on the basis of two factors. The first is the heart rate, the second is the morphology. In the case of heart rate, as I have said, that being normal varies from patient to patient. So we consider, as per some of the journals and literature, if the heart rate is between 60 beats per minute to 100 beats per minute, we say that the heart is working as normal. If the heart rate goes beyond 100 beats and is in between 150 beats per minute, then it is a case of simple tachyarrhythmia. If the heart rate goes above 150 to 250, then it is a case of tachyarrhythmia or paroxysmal tachyarrhythmia. And if the heart rate is above 250 beats per minute, then it is flutter, which I was talking about. And if the heart rate again goes beyond 350 beats per minute, then it is a case of fibrillation, which is very unfortunate for a patient. Similarly, if the heart rate goes below 60 beats per minute, then it is a case of mild bradyarrhythmia. If it goes below 40 beats per minute, it is moderate bradyarrhythmia. And if it goes below 20 beats per minute, then it is a case of severe bradyarrhythmia, which is also unfortunate. So more or less, all these classification on the basis of heart rate beyond normal, means if the heart rate goes above 100 beats per minute, then altogether, collectively, it is known as tachyarrhythmia case, and below 60 beats per minute, it is known as the bradyarrhythmia case. Now, on the basis of morphology, as I have said, that heart has 4 chambers and it undergoes 3 processes. So either there will be problem in any of the nodes or any of the processes. So if there is any problem with the sinoatrial node or the rhythms which is generated from the sinoatrial node, it generates sinus arrhythmias. Arrhythmias are nothing but the abnormalities inside the heart. So further classification of sinus arrhythmias can be sinus bradycardia, tachycardia, tachybrady syndrome. So sinus bradycardia means there is a problem with the sinoatrial node, first of all. And due to that problem, the heart rate is going below 60 beats per minute. Similarly, when there is a problem with the atrial myocardial tissue or the atrias, which are the upper chambers, it leads to the generation of atrial arrhythmias. And further subclassification is atrial tachycardia, flutter, and fibrillation. So the heart rate may fall below 60 beats per minute, or it may go up also for the flutter and fibrillation above 100 beats per minute. So if there is any problem in the AV node, which is the atrioventricular node, then it leads to the generation of junctional arrhythmias, and it is further subclassified into first degree, second degree, and third degree heart blocks. So I have just taken a sample from Google because it has a ECG sheet and it is being plotted by the machine. So you can see that a typical ECG typically looks like this. It has P wave, QRS wave, and T wave. But here there is a blockage. There is an isoelectric line and it has no wave generated in between. So that is a case of second degree heart block. In case of atrial flutter, we know that the atrial depolarization results in the generation of P wave. So you may find in case of atrial flutter that flutter, the heart rate goes beyond 250 beats per minute, and there is a problem in the atria. So you will find that there is no generation of P wave in the ECG. So this graph reflects that the person is suffering from the atrial flutter. So what we are going to study in this lecture is we are capable of identifying 15 or 16, we can say, ECG signals, among which one is the normal, and 15 other classes of arrhythmias or the abnormalities. They have a medical name like left bundle branch block. In short, it is known as the LBB, RBB, APC, PVC, preventricular contraction bit, and similarly in total there are 15 number of arrhythmias along with normal. In this lecture we are going to identify them. So now coming to the what existing systems we have and what advancement we require. So currently Holter machines are available, and this has been reported in a paper. This was published in IEEE Transactions on some paper. So the basic theme of the Holter machines are the signals are only being captured by the machine and no analysis is being done. Means only storage can be done using the Holter machine and no feedback it gives. It gives no feedback. The data is being analyzed by a physician in offline mode. So it stores the data for 24 hours. Coming to the loop recorders, only recording is performed up to an extent of 3 months. Rather, no real-time classification is performed. The difference between Holter machines and loop recorders are that Holter machines is capable of storing for 24-hour data and loop recorders can store up to a period of 3 months. There are some partial devices which provide some partial feedback also, like there are smartphones, PDAs, and Vitaphone medicine system active ECG, which sends the signals to a remote place, and that is analyzed by a cardiologist, and we call it as remote real-time monitoring. So now I will try to go very fast. So more or less what I want to highlight is there is no such device available which is capable of classifying 16 different kind of ECG signals in real time at the place of patient. Some partial things are being done by the Apple Watches, or there are more companies that have developed the smart watches in the case of smart watches, but more or less they are providing only the heart rate and some partial feedback is being given by those devices. So coming to the next slide, that what is the motivation? So the devices performing ECG monitoring are huge in size, like what we have talked in the case of Holter machines, and they are restricted to ICUs in high-tech hospitals, and they are pretty costlier for common people. To the best of my knowledge, there is no such device which is available for common people with low cost for continuous real-time monitoring and diagnosis of cardiovascular diseases. Therefore, there is a need of a low-cost portable device for real-time and automatic diagnosis of cardiovascular diseases. So to develop such a device, there is a need of some efficient algorithms, AI-based algorithms. And if we want to develop a device, we have to first of all develop a hardware prototype for that. And to develop that, we have implemented the algorithm on ARM-based processor. So we have studied some of the signal processing techniques also, machine learning algorithms, and we have implemented all together on the commercially available microcontroller platforms. Coming to the objective part, we study and proposed new efficient methods for feature extraction and classification of ECG signals to develop and hardware using embedded hardware platforms. And finally, we have fabricated a PCB-based customized hardware that is used to implement a selected efficient method. Means we have developed 4 or 5 combination of algorithms, and the algorithms which is efficient. Efficient means in terms of accuracy as well as the computational complexity. So if the algorithm is being implemented in real time, they have been implemented using the microcontrollers, and among the efficient method, it is being fabricated also. So in this figure, we can see that the ECG signal has been gathered through the ECG lids, and the data is being fed to the embedded computing system. In this embedded computing system, this is typically a microcontroller, ARM-based microcontroller. And in this, we have done the pre-processing or filtering of the ECG signals, R-peak detection, which we were talking about the QRS wave. And then after, we have done the feature extraction and classification. And this all has been programmed and put into this embedded computing system. And then after, the results of implementing all these stages of methods, the output is being displayed on the monitoring device, which is typically in our case is 16x2 LCD or 7-segment display. We have taken both for the displaying of the classes of ECG signals. We will see this in a bit later stage. So this is the scope of the work, that first of all, the methods have been simulated in MATLAB to see and check the accuracy, whether it is feasible or not to implement in the hardware, because we want the results in real time. Secondly, we have validated our methods over publicly available open source MIT BIH Arrhythmia database in laboratory experimental setup. The design, which is the PCB-based customized hardware device, which is being displayed on the right-hand side, is designed in-house and being fabricated, means the design file, the Gerber file, has been outsourced to a company for fabrication. So on the left-hand side, we can see that this is a laboratory setup of all the components which has been used. Like the real-time ECG signals are being generated on the arbitrary function generator. It is a two-channel arbitrary function generator. Its input are being sent to the ARM processor, which is my R9 embedded development board. And in this embedded computing system, which is my ARM, we have done the pre-processing, R-peak detection, feature extraction, classification. And it is developed using C++ and embedded C also in both the languages. And the output of this ARM processor is being displayed. In this case, we have used the 7-segment display, and it is showing APB bit, means atrial premature contraction bit. And the morphology, means the appearance of the signal, is being displayed on the MSO, mixed signal oscilloscope. And on the right-hand side, it is just a snapshot of the fabricated PCB-based handheld device. And in this, it has been shown that a normal bit is being detected by this hardware, customized hardware, and it has no alarm being generated, so no abnormality or no arrhythmias is being found out. So first of all, we will study the literature, what methods are available, and what we are capable of being developed. So there are several methods reported in the literature, like Fourier transform. Some of the authors in 1999 have used the Fourier transform to extract the features of the ECG signals, short time Fourier transform. So every method has its own advantages and disadvantages. Like the Fourier transform provides the frequency components, as we all know, but it fails to provide any information about the time of occurrence of the frequency components. In the case of short time Fourier transform, it overcomes the limitations of Fourier transform. As such, it provides a constant window, but the selection of size of windows remains a challenge, because ECG is a non-stationary signal. So there may be a probability, let me give you an example, that while I am sitting, my heart rate is around 82 to 85 bits per minute, and it is normal. But while I am running, my heart rate goes beyond 100 bits per minute, approximately 105, 110. But that is not a case of abnormality, that is a physical change. So what I am trying to say is that in both the conditions, I am having a normal heart rhythm. So the nature of a normal signal may vary from patient to patient. And that's why I am saying that an ECG signal is a non-stationary signal. So if I am running holding a device, and if I am sitting holding a device, having a fixed window to analyze any ECG signal can be a false statement. So it should not be bounded that the window should be of fixed size. So to overcome this, some researchers use the wavelet transform. It uses longer windows at lower frequencies and shorter windows at higher frequencies. But in this case also, selection of mother wavelet and sampling frequency for extracting the frequency components is a major factor, failing which it may lead to provide a misleading information. Means actually what happens is, while we are going to implement the wavelet transform, we have to choose a mother wavelet. So that selection of mother wavelet should be data dependent, not user should define it. So if we are not choosing properly the mother wavelet or the sampling frequency, then it may lead to a misleading information. Talking about the Stockwell transform, in this case also the choice of window parameters are being selected optimally to preserve both the time and frequency information. However, it is computationally redundant. There are other more methods like EMD and HST, empirical mode decomposition. It is extremely influenced by the noise associated with the input signal, and it is having high computational complexity. Means the number of operations used to implement this EMD algorithm is large in comparison to the other algorithms. And similar is the case with the Hilbert-Houarn transform, that it is also having high computational complexity. Talking about the machine learning methods, these all were the feature extraction methods which are being used to extract the features. And the input of these features are being applied to the machine learning methods. So you also know that there are several existing machine learning methods like ANN, support vector machines, K nearest neighbor, and K means clustering. So all of these have their own advantages and disadvantages, but more or less what I want to highlight is everything must be data dependent. It should not be like if I am the program developer and I want to use this parameter fix for any kind of data, then it may or may not result good. Like in the case of artificial neural networks, we have to choose for number of hidden layers, and that is purely user dependent. If I want to use 10, I will use 10. If I want to use 11, I will use 11. And there may be a possibility that 10 will result, the result of using 10 number of hidden layers may be good or maybe 11. So I don't know. I have to check it manually that what should be the number of hidden layers in the case of artificial neural networks. In the case of support vector machines also similar is the case. When you will go and implement, you will find that there are 4 kernels and you have to choose among the best. So whenever you will read papers, you will find that many of the researchers have also reported that I have used this number of data, and for this number of data, I have implemented all the kernels, and among all the kernels, this kernel for this type of data reported the best accuracy. So we have to actually manually check, and these all parameters are data dependent. It is not fixed that the data which I am using, which is the open source database, which is the MIT BIH, or once it is developed for a particular parameter, it is not necessary that it will work good for the data which I have captured using my device from patients directly. So that has to be looked upon while developing such algorithms or such device. And there are more on the literature survey that the people have used the wavelet transform and decision tree algorithm, and they have classified 5 classes of ECG signals and reported 96.128%. So similarly, many algorithms have been proposed in literature, and very good accuracy in means in the current situation has been developed, but more or less it is not feasible to implement them on a real-time basis. The companies are still working very hard to do it. So these are the proposed works which you are going to see in this lecture, that we have extracted the RR interval features and we have used the knowledge-based approach to classify 4 abnormalities, including normal, and PCA and means the principal component analysis along with BPNN, which is the back propagation neural network, is used to classify 6 number of ECG classes. And similarly, we will look at each of them one by one. So first is the study of knowledge-based arrhythmia monitoring system. So in this case, the ECG signal is being fed as input. There is a pre-processing stage in which the linear and the non-linear filtering has been done. We will see this a bit later. And there is a decision stage followed by the pre-processing stage. And finally, this features have been, or the features extracted are being given as input to the knowledge-based classifier for the identification of bits. So more or less there are 3 steps: the pre-processing, decision, and the classifier stage. In the pre-processing stage, we have done the linear filtering and we have implemented the high pass and the low pass filters using this difference equations. And then after, we have applied a derivative operator to identify the slope of the wave. And we can see that in this image that this is a raw ECG signal, and after being cascading of the high pass and low pass filters, the signals are being filtered. After the pre-processing stage, the non-linear filtering is being done, like it has been squared and a moving window integrator has been placed. And then after, the thresholds are being used to detect the peak of the R wave. Why it is very essential to detect the peak? Because the other waves, as I have said, that the P, QRS and T wave, out of these 3 waves, the QRS wave was the most important having feature that it has the maximum amplitude among in respect to the other 2 waves like P and T. So it is quite easy to detect the R peak, and based on the R peak, means in this we have applied the thresholds and detected the R peak, and after being detected the R peak, we have implemented an algorithm, and this algorithm was not proposed by us. It has been proposed by Tiporus et al. In 2022. What we contributed in this work, that what the method he has proposed, like as you will see that a window has been taken, and using the window, if it is identified using a second window, then it is identified as a normal category, and based on that he has proposed 3 rules. So these 3 rules have been developed in C programming language, and then after we have implemented this algorithm on the FPGA chip. So it is basically a hardware soft, means the FPGA chip is on the hardcore, means the chip is available on the board itself, while the TSK, Texas Instruments processor, we have used the IP core of that processor to develop this hardware prototype. So in that we have to develop the software or the interfacing, what we want to use, like you can see that we want an ADC. So ADC has been used and it has been connected through SPI to this processor, and we require a DAC to see what input we have taken and what is being displayed as the output. So we require both of these components, and we have designed this complete system. And the algorithm, as again as previously I have said, is being developed in the C++ programming language in the Altium designer environment. This is a board which contains the FPGA chip in the board itself, and it gives us some of the IP cores of the processors. So how this thing has been implemented can be seen through this image. Like FPGA based SoC has been developed in the prototype base, and analog signals are being generated. So through the text file, means whenever you will see the MIT BIH database, they have given the amplitude values in millivolts. So you can just load it on the MATLAB also, and you can generate it in real time also. So we have just written those values in a text file and fed it to the arbitrary function generator as input, and the real time signals are being generated. And the output of this real time function generator is being taken to the Altium Designer board as input on the ADC, and the output of the bid classification is being shown on the TFT screen, which is integrated with this board. But we have to write the code for this also. So in total, we have taken 10,800 bits, in which we have considered 6,000 as normal, 4,000 PVC bits have been taken, and ventricular fibrillation bits were 400, and 2-degree heart blocks were 400. The predicted output classes by the developed platform are being displayed on the TFT and compared with the re-annotated file for formulating the confusion matrix. So this confusion matrix is actually the result, because there are two things. First of all, what is being means the result, what the doctor has predicted, means I am saying that there are 6,000 bits, but I am not a doctor. So the person who has classified this 6,000 bits into the normal category is termed as the ground truth, and it is not going to change because it is being classified by an expert. And secondly, out of these 6,000, what my system is giving is known as the predicted bits. So in the confusion matrix, we can see that out of 6,000 bits, my system, what I have developed, has correctly classified 5,921 out of this 6,000 into the normal category, and 61 into the PVC, 13 into VF, and 5 into 2-degree heart block. Similarly, for the PVC, which was originally 4,000, out of this 4,000, 3,878 is being classified into the PVC category, and the rest, among the rest, 97 is being classified into normal, 17 into ventricular fibrillation, and 8 into 2-degree heart block. And similarly, so finally we calculated the accuracy of this complete system, and the accuracy is around 97.98%. So there are two medical parameters what you may also have heard during the COVID-19 period, that the sensitivity and the specificity of RT-PCR. So the sensitivity is defined as the correctly detected events among the total number of events. Let me define this in a layman language, that sensitivity detects the number of diseased people out of the total number of people, while specificity determines the number of normal patients. Suppose we have a total number of 100 patients to be studied. Out of that, 70 are diseased and 30 are normal. So 70 will be the sensitivity and 30 will be the specificity. And positive predictivity is the rate of correctly classified events in among the all detected events. So this is a brief calculation which is based on the true positive, true negative, false positive, and false negative. So the sensitivity of this complete platform is 97.72%, specificity is 99.09%, and positive predictivity is 96.46%. So we can say that out of 100, 99% of the normal patients are being identified as normal by our platform. And out of 100, 97% of the diseased people are being identified as diseased by our platform. So further we have done the comparison. Since it was existing algorithm, so it doesn't make a good sense So in this case, we have further developed many of the algorithms like the principal component analysis and the BPNN, backpropagation neural network. And further, we have implemented the fast Fourier transform with discrete wavelet transform. And both of these features are put as input to the backpropagation neural network. So this is the basic block diagram of this machine learning network. The pre-processing RFIC detection is common to all the methods, and the feature extraction and classification methods have been changed on a regular basis. So a 12-tap FIR low-pass filter with a cutoff frequency of 35 Hz is used here to remove the high-frequency noise and power line interference. And I have discussed the Pan-Tompkins algorithm, which is used to detect the R peak in the previous work. Now, coming to the PCA, it is followed by some of the procedures, like it has the steps like we have to standardize the data by reducing the mean. We have to compute the covariance matrix. We have to find the eigenvectors. We have to sort the eigenvectors. And we have to project the eigenvectors into orders. What our contribution to this algorithm is, again, we have implemented this PCA algorithm in the hardware, that is ARM-based microcontroller platform. And secondly, we have modified the PCA algorithm and we have chosen the cyclic Jacobi technique due to its simplicity and accuracy to compute the eigenvectors for a symmetric matrix for faster convergence. So we have combined the standard PCA method and we have used this cyclic Jacobi method, and the components, means the output of the PCA is the components that are being calculated are uncorrelated and orthogonal to each other. So in this case, we have extracted 5 principal components to represent each ECG signals or heartbeat. These are the number of heartbeats. So these are the name of the files which you will find in the MIT BIS database. Among this, 4,200 beats are being selected. Out of this, 200 bits are selected for the normal category for training purpose, for the development of the classifier model. And we have tested the method for 4,000 normal bits. So in total, the bits taken for training and testing contains 900 bits for training and 15,200 bits for testing. And it is to note that both these data are different from each other. It is not like, since it has a lower number, so the same data is used for training and the same data is used for testing. Both the data sets are different from each other. So again, in this case, we can see that there is an ARM-based microcontroller platform. Again, the ECG signals are being generated in real time using the arbitrary function generator. And the results are being displayed on the 7-segment display and being displayed on the DSO. All the things are same, only the method has changed. And you can see the complete setup over this. So this platform is being generated in real time and regularly the data is being given as input and being supplied to the microcontroller platform. And you can see this complete laboratory setup in this video. Coming forward to this is again the confusion matrix. So we have implemented the method, the PCA based BPNN algorithm, and we have achieved a 92.8% of accuracy. While the sensitivity is 97.57%, specificity is 99.59%. Coming to the FFT-based DWT algorithm. So DWT algorithm is existing. What we have did in this method is, we have reduced the computational complexity of this DWT method, that is discrete wavelet transform. And the calculation of DWT we have made through the FFT-based algorithm, fast Fourier transform. So pre-processing R peak detection will remain same. The standard Pan-Tompkins algorithm is being used to detect the R peak. It has been regularly used due to two factors. First of all, it has the highest accuracy reported in the literature. Secondly, it has the lowest computational complexity. So we have also written a review paper and that has been published in Springer. So the result of this, so this is actually the architecture. If we will see that how this FFT-based DWT implemented, FFT-based DWT method has been implemented. So we have first splitted the even and the odd index sequences. Then after n length FFT is performed on each decimated input. And 4 frequency domain convolutions are being performed on multiplying the Hermitian symmetric matrix, which is of the FFT of the input and the filter. This requires 4n/2 complex multiplication for the full filters. And finally, 2 blocks are being added and 2 inverse FFTs are applied. In comparison to the classical DWT, means the conventional or the discrete wavelet transform, which is implemented by cascading of high pass and low pass filters, the comparison is evidently in favor of FFT version of the DWT, because as the signal length is going to increase beyond 16, we will find that the execution time of the algorithm is very less. So in this case, the length of the ECG signal was 256. So we reported that the computational complexity is this much and we require this much number of computations to perform this FFT-based DWT algorithm. So finally, we obtained 18 coefficients as one feature vector to represent each of the ECG signals. And then after, again, we use the BPNN network to classify this, and finally it has been implemented on the commercially available hardware platforms. These were the number of training set and testing sets. We actually regularly develop newer algorithms and we varied the number of training data and testing data. In this case, we have replaced, okay, this video I have seen. So the accuracy of this method is 97.4% and the sensitivity and specificity are 97.59% and 99.59% respectively. So
Excuse me, sir.
Yes, ma'am.
I think the slides are not changing.
Okay. So you should say, right? So finally, we compared our proposed algorithm with the existing methods and we got the highest accuracy, and we classified more number of classes with respect to the existing works in the literature. Coming to the more algorithms, we have proposed DOST, discrete orthogonal Stockwell transform, and DCT based DOST. We reduced the complexity of the DOST algorithm and we classified this using the twin support vector machine. If you will study the support vector machine, there are several concepts that has been given. And in this case, these are the hardware results for pre-processing. So on the left hand side, it is the noisy ECG signal, and on the right hand side, we have filtered the ECG signal. And for filtering, we use the median filter, which removes the P wave, while the second median filter removes the T wave within the ECG signal. The output of the second median filter is subtracted from the original signal to generate the baseline corrected signal. And finally, a 12 tap low pass filter is being used with equal ripple in the pass band stop bands to filter the ECG signals. And consequently, the R peak is detected. And after detection of the R peak, first of all, we have implemented the DOST algorithm, which is the existing algorithm, discrete orthogonal Stockwell transform, and it is implemented using this equation. The running time complexity in factoring DOST using FFT. A classical FFT is used for the implementation of DOST, and in the future work, what we did is we replaced this FFT block by the DCT block. So if we calculate the DOST using FFT, we have a complexity of the order of n log n. So an ECG signal of length n is passed through the n point FFT stage, and we have received the FFT coefficients as F1, F2 to Fn. Then they have been partitioned into the subbands. Beta point inverse FFTs are being applied, and consequently we have calculated the features using the DOST method, and we implemented the SVM technique for the classification of these features, and finally we again implemented this method into the hardware platforms. So we achieved an accuracy of 96.29%, sensitivity of 92% and 95.83% respectively. And we compared this method, and this work was published in Nature Scientific Reports. And further, what I want to show you is I modified the standard DOST algorithm in which the FFT block was used. This was been replaced by the DCT block. So what we achieved is we have reduced the execution time of this process, or we have reduced the computational complexity of the standard algorithm, and in return we have achieved an accuracy of 97.59% and specificity of 99.59%, which is more in comparison to the standard DOST algorithm. So I have shown you 4 proposed algorithms, and among the 4 proposed algorithms, this is the summary of this DCT, BS, DOST, and we achieved this much of accuracy. And finally, we want to develop a customized hardware. So we use different components to develop a device, and this is the device is being developed. Eagle software was used to design this 2-layer PCB, and it is developed in-house or designed in-house. There is a fabrication company which is known as the PCB Power, which is based on Gujarat. We sent the design file there for the fabrication. And finally, the length, means the dimensions of the device is 90.42 mm and 60.83 mm respectively. And again we revalidated the algorithm after the implementation. Accuracy almost remained same, and this is the complete setup. We replaced the commercially available platform for this much size of device. We are making further improvements, and we have reduced the length of the device, length and width of the device. And after reducing the length and width, coming to the major contributions, that we have developed this number of algorithms. And what I want to remind you regarding the future scope or the future work, what you can do is that we have used a fixed length ECG signal, which is not actually the case. We can use the variable window. So in future scope, you can use the variable windows. You can go for the deep learning techniques like convolutional neural network or the recurrent neural networks, RNN. But you have to make sure that the output should come into a real time. The study can be extended to classify more number of abnormalities, and finally, it can be developed into a system on chip based concept. So these are the number of publications that has been published by me in this topic. So there are a lot of publications. The patent is also under process, and these are the references which have been studied to undergo all of this work. So I have 7 minutes left, so it's all from my side. I will love to take questions from your side.
Yes,
Yes, sir.
participants, if you are having any question, ask them, sir. I have some question. Anyone? Okay, everything is clear. So thank you so much, Dr. Sandeep Raj sir, for your valuable time. Your expert talk has provided us with invaluable insights about development of hardware prototype of an efficient method for handle arrhythmia monitoring device. You talked about cardiovascular disease, ECG, arrhythmias. Then you informed that the detection and treatment is very costly and how you have developed a cost-efficient for that. You showed us the different signal processing technique, feature extraction method, classification method, and the proposed methods of arrhythmia classification, and how you implemented the knowledge-based approach. I am sure our participants have attained a better understanding about all these topics. Thank you so much, sir, for talking about your for giving your valuable time to impart us with your knowledge. Thank you, Sandeep Raj.
Thank you, sir. Thank you.
Okay, okay, participants, you may leave it. Thank you. We will meet by tomorrow, 2 o'clock. Means before 10 minutes, 1:50. Thank you, everybody.
Thank you, sir.
Thank you, sir.
Okay.
Thank you, sir.
Okay, everyone will leave it. Thank you.